Okay, hi everybody. All right, so we're going to continue talking about vision. Um, so remember I was talking about how our eyes constantly move, and what is the reason that our eyes are constantly moving around, even if we think we're looking at one fixed object? Why do we need our eyes to move? What would happen if they didn't?
Wouldn't we have blind spots?
Yes, we have blind spots, and if if our eyes were able to stay perfectly still, parts of images would disappear, right? So I have some images that will help you know for sure that our eyes definitely don't stay perfectly still. So if I ask you right now to start at this center point and without using your cursor or your finger or anything, just using your eyes, count the number of dots between this center spot and the last spot on the right. Is that easy to do? No, it's not easy for me to do. And that's because your eyes are moving. And that's why you need to do things like put a piece of paper over it and slide it over slowly, or use your cursor to count each one. If things are further apart, they're easier to count. That's because your eyes are constantly moving around to make up for that blind spot. Here's another example. Stare at this center circle and try to look directly at where the dark part, the dark semicircle, meets the light semicircle. And just stare at that for a little while. Now, what optical illusion occurs?
Everything is moving.
Right, things start moving, particularly inside these darker rings. It appears that the, sorry, it appears that the atmosphere or whatever space inside these dark rings is moving around in a circle, doesn't it? And is it? No, the image is fixed. It's your eyes that are moving around. And when you want something to look like it's moving, it really helps to have stripes near it. Okay, because your eyes are moving back and forth, and it gives the impression or the perception or interpretation of things moving. So the image isn't moving, it's your eyes moving, and you're perceiving it as movement when the movement really isn't there.
A question.
Mhm.
Is it weird that like right when you put it on that slide, I instantly saw it moving? Like I didn't even have to stare at it.
No, that's fine.
That's fine.
And it changes on the day. So I've shown this, probably 40 times. And some days I barely see it moving, and some days it's spinning like crazy.
Gotcha.
That's kind of an example of priming and, where you're at that day, how alert you are, so you're probably just ready to see things right now. Yeah, you're probably pretty alert right now. Okay, this is called Troxler's fading. So, you can see that a one of those pinkish purple dots is disappearing. Okay, and doesn't it give the impression of the image going in a circle, like that there's a circle with one dot missing and it's spinning? That's just your perception of something that's not necessarily there. You know, when they built this image, they just had a series of dots disappear at a certain time, right? The other thing is, the other kind of illusion that happens is stare at the plus sign right in the middle for a little while. And a couple things happen. So can someone tell me what happens when you stare at the plus sign in the middle of the ring there?
At least in my case, the circle that just goes around, it has color now.
Yeah, one thing is it has color, and we're going to talk a little bit about, you know, the color theories, why we see certain colors. And one theory is that, you know, we have cones that perceive red and green, and you only perceive one of those colors at a time. And when one is fatigued, you'll see the after image in the other color. So green is the opposite of red, and you'll see green's the color you're seeing, right? Like a lime, kind of like a light lime green. Okay, so that's one of the effects. Did anybody else notice something weird? If you stare right in the center, what else happens? If you make it as big as possible and look right in the center, trying to, oh, did I stop it? Oh, started again. And don't focus on the outside dots, okay? Try to not pay attention to the outside dots and just look at the plus sign. You don't have to try this one.
They're fading.
Yeah, they kind of went away from me too.
Right. So literally, you know, the way it's built, only one of those dots is disappearing at a time. But while you're looking for a while, after you look for a while, more of them disappear, right? And it's not because the program is changing, right? It's because of that blind spot. It's because of habituation, right? So it's a combination of these things that we've been talking about that happen in visual sensation. That's called Troxler's fading because Troxler's the one who demonstrated it. All right. All right, so I have a clip that I think does a better job of describing the two theories, the two main theories of how we process color in vision. And they used to be competing theories, but now most people agree that we use both of these ways of processing color. So let's just open. Okay, can you see the screen where the, oh, I stopped sharing, didn't I? Okay. Okay, now can you see the big eye?
Yeah, we can.
Good. Get full screen.
Color doesn't exist. Not really. Right now, you're probably thinking something along the lines of, well, I can see color. This will lead you to one of two conclusions. Either this statement is completely crazy, or that you're incredibly special. Actually, there's more at work here than that. What we perceive as colors are light waves of different frequencies that bounce off of objects, enter specific receptors in our eyes, are translated into an electric signal, enter our brains, and are translated as color. It's a complex process, and scientists have developed a number of theories to explain how it works. One of these models is called the opponent process theory. The opponent process theory, developed by Ewald Hering, is one of the two basic models explaining how we see color. But to understand it, we have to talk about the other model first. The trichromatic theory basically states that in our eyes, there are three kinds of photoreceptors called cones. Some cones can only receive light waves of short frequencies, resulting in the color blue. Others can only receive medium waves, resulting in green, and the others can only receive long waves, resulting in red. So blue, green, and red cones receive light of different wavelengths and translate them into signals the brain can understand as color. The trichromatic theory is very popular, but it doesn't seem to explain everything. Enter the opponent process theory. This model describes the relationship between the cones to explain how they form a spectrum of colors. The basic idea is that cones are linked together in opposing pairs. Only one cone in each pair can create a signal for the brain at a time. Let's ask ourselves this. Have you ever seen a color that wasn't quite blue but wasn't quite green, a bluish green? Sure we have. That's because the cones for blue and green aren't opposing pairs. They're able to fire at the same time. However, have you ever seen a color that's sort of yellow and sort of blue? No, there is no yellow-blue, just as there is no reddish-green. Red and green are opposing pairs. Only one of them can be firing at a time. You can see blue and red together, or blue and green together, but not green and red. This theory also explains how
I just want to point out that this is when light waves mix. This, if anybody does art or paints here, you might be thinking, wait a minute, you can put these colors together and get a different color. It's different from mixing pigments. Okay, they're talking about when light waves of different frequencies get mixed together. Okay, and light waves are just like, think of them as waves in the ocean. They have different frequencies, right? And different amplitudes. And the frequency is kind of how fast they're coming, right? And a short frequency is, a shorter wavelength between two waves, right? And a longer frequency is a shorter length. I mean, a longer length between two waves. So the shorter ones are blue, the medium ones are green, and the longest ones are red. And the way I remember that is in terms of cool and warm colors, which is a cool color, blue or red?
Blue.
Red is warm, cool is blue.
Yeah. So if blue is a cool color, think of temperature, right? It's lower temperature, shorter wavelength, smaller number, okay? If red is a warm color, it would be a higher temperature, a longer wavelength, bigger number. That's just how I remember it.
we can see the color yellow. Yellow is a primary color, meaning it's not composed of any other combined colors. So how can we see it if there is no cone for yellow? Yellow is the opposing pair of blue. So as long as the blue cone is active, the red and green cones can't send signals to the brain that can be translated as yellow. However, when the blue cone is inactive, the red and green cones can receive yellow light, which has a medium-long wavelength, and transmit that signal. But the minute blue comes back on, this is inhibited. You can only see blue or yellow in a single spot. They can be next to each other, but not overlapping or mixing. In a similar way, the balance of signals between all three cones produces the colors of black or white, but never both simultaneously. Thus, our three opposing pairs are red, green, blue, yellow, and black, white. There's actually a very simple experiment you can do at home to test the opponent process theory. For this, you will need red, blue, and white sheets of paper. Cut out a small blue square and place it on top of the red paper.
All right, so you can just stare at it. If you have something white nearby, like a white wall or a piece of white paper, I'm gonna grab a piece of white paper. Just, get rid of the gallery view for a minute and stare at the blue dot. I mean, the blue, sorry, it's usually a dot. Stare at the blue square for a little while. When that square starts kind of floating around, you're starting to have stared at it for too long. And after we stare at it for a while, we're gonna just not look at anything else and quickly look to the whitest thing in our environment. You see different colors? What colors do you see if you look at something white?
I kind of saw like the blue, like I don't know, it kind of looks like the blue square almost,
Mm-hmm. The
like
outside.
kind of yellowish green.
Uh-huh. Yep, the outside does, right? And then the inside color, I think she says it's a different color than I saw. But what do people see for the inside square?
Yellow.
More like a orange.
Yeah, like I see like an orangey, but I think she says it's yellow. But you know, everybody's a little different.
I saw yellow.
Placing the white paper to the side.
Yellow.
Now, stare at that blue square. Stare at it really hard for 30 to 60 seconds. Your eyes should start to feel sore. Then look quickly over at the blank sheet of white paper and blink. Did you see that?
Oh,
For
now
just
it's
an
yellow.
instant, most people will see a green sheet with a yellow square in the middle. This optical illusion is called an after image. So what just happened? By staring at the flat colors of red and blue, you exhausted the red and blue sensors in your eyes. Then, when you looked away, those cones took a break, meaning that for a split second, only their opposing pairs were working. To see white, all the cones need to be transmitting a signal. So in that instant, the brain was only receiving the signals for green and yellow, the opposing pairs of red and blue. And that's what you saw. You can recreate this experiment in a myriad of ways. Place blue and yellow squares next to each other. And when you look away,
You want to do this one for a minute? See what you see. So what happened, you know, when you think about it, probably when you look down at that paper, it was kind of an aqua color. Was it for you guys? Or if you looked at a white wall, was it a bright blue on the outside or kind of a greenish blue? For me, it was like light turquoise. You know, so she's saying that it's because the blue from staring at that blue square got exhausted. So you had to rely on your green cones more. But all right, let's stare at this blue one in the middle with the yellow squares as much as we can for like 30 seconds. You know, and we'll probably get some after effects from the red and white too, but let's just stare at this for a while. Really, like you stare at it until your eyes kind of hurt, because that means that your cones, the color receptors in your retina, are getting tired. Just keep staring at it. And you can kind of start seeing after images of the smaller squares kind of floating around, but keep looking. Keep staring as long as you can stand. And quickly look away to something white. Okay, so did you see an after image? This one wasn't as strong for me. Did other people have a strong after image?
At least for me, the yellow squares are now blue and
They were much darker.
completely yellow.
Uh-huh. Okay. So she just talks about a bunch of experiments you can do.
sheet. Then look away and watch them all reverse.
Yeah, so
Color
they
is a matter
reverse.
of perception, and the opponent process theory helps us understand how that works. Okay, let's take a moment to review what we've learned. The opponent process theory is a model to explain how the mind perceives color, while the trichromatic theory postulates that color is first received via waves of light entering red, blue, and green cones in the eye. The opponent process theory explains how these cones are neurally connected. Opposing pairs consist of two colors that inhibit each other, meaning that color can't be seen in the same space at the same time. It's one or the other. The opposing pairs are red-green, blue-yellow, and black-white. The results of this can be seen in optical illusions called after images. created by fatiguing one cone to overstimulate the other. Understanding this theory will help you look at colors in a whole new way.
Okay, so does anybody here have color blindness that you know of? Sometimes I do the test in class and somebody finds out that they have color blindness. I did it with my family and because I had some suspicions that my husband was colorblind, and he's pretty severely colorblind. And does anybody know which color receptors it tends to affect most?
Red and green.
Red and green, yeah. So it's some kind of genetic difference, usually in who?
Men.
Yeah, it's more common in men, whereby the cones that are responsible for red and green, which are thought to be, the opposing colors, aren't as good at discriminating red from green. Okay, so in those pictures, have you seen the pictures that have a bunch of dots and you have to pick out what number is represented inside a circle by like green dots or whatever? Those are really hard for people with red-green color blindness to read. All right. Stop sharing that screen. Go back to PowerPoint. All right, so this is just a summary of what you saw in the video, and I just really left it there so that you can use it for your studying. Okay. For this one, I want you guys to use chat, and let me make sure I can get chat up here. Bring it to the front. All right, and I want everyone to, do you guys all know how to chat like directly to me and not to the whole class? Does everybody know how to chat privately? You just pull down where it's like, it might say to everyone. You'd pull that down and just select my name, which is Amy Cirillo. Okay, and then, so I'm gonna put, slide number 1. And you guys are all gonna individually text me what you see in the slide. Okay, just tell me like the basic thing that you see in that picture.
So we need to do that right now?
Yep.
Okay.
And it's just what we see in this picture.
Yeah, just a basic, just a couple words. Everybody go. Okay, now I'm going to show you another slide. Tell me what you see in a direct message. Oh, wait, sorry. Slide 2, thank you. Did everybody put their response yet? What do you see? Picture.
Are we responding for the second slide as well?
Yeah, this is just this slide. So slide 2, what do you see? The one that has a 2 up here. Oops. Damn. Oops. Sorry, everyone. My mouse gets away from me sometimes. This mouse. All right. Now I'll remember to write slide 3 before I change it. And you guys are going to write what you see here. Let's see if everybody. There should be a few more people. Is there anybody who hasn't answered? Okay. So that was slide 3. Did I actually write it this time? Okay, and now the next one will be slide 4, and write what you see here in private messages to me. Sorry. Is that everybody? Okay. Okay, and then the next one is slide 5. Okay, did everybody put their image? Okay, so we're going to do another series of slides too, another series of 5 slides. So this one, again, we'll start over at slide 1. Oh, and I have to show it to you. Thank you.
Are we once again just writing what we see?
Yep, same thing. Okay, now let's do the next slide. Can you guys see where I write slide 2? Okay, because it says everyone in waiting room, which is weird. I got like 16. Should have more. Okay, is this slide 3 now? Yeah. So I'll do slide 3. I'll tell you what you see here. Oops, sorry. Now we'll do slide 4. Okay, so don't text me for a minute. I'm gonna just count something up, count some stuff up. Okay. All right, so let me go back. Oops. All right, so this slide, there were 30 answers, and four people saw a man's face, and 26 people saw a mouse or a rat. Okay, so the people who saw a man, can you see a mouse or a rat? This is the ears. This is the snout. Some people thought its mouth was open. Some people thought this was like the front paw. This is the mouse's back. This is the hind leg, the belly, and here's the tail or the rat. And then if it's an old man, these are his spectacles, his eye, a big hook nose, upper lip, jawbone, and hair and ear, and the head. Okay, so can everybody see those now? Okay, so I've shown this a million times, and I always say, which one you see is your perception, right? We all have the same sensation, based on our, the quality of our vision and if we have a vision impairment, but the same light waves are bouncing off our screens and hitting our eyes, right? But what we perceive has to do with priming, has to do with, what we've seen before, what our history of viewing sketches is, right? What we're likely to see based on our history of seeing. And I've always said, so if I had shown you a long series of pictures of mice or rats, more of you probably would have seen the mouse. And this is definitely more people saw a mouse or a rat versus the man than usual. Is anybody like pretty sure they would have seen the man first if they hadn't seen all those pictures of mice or rats? Anybody feel like they maybe would have seen the man first? It's really hard to know, isn't it? All right, so let me just count up the next one. All right, so the next one I want to look at is this. Okay, 30 people answered. One person saw a bear, 12 people saw a dog, and 17 people saw a man running into the woods. And what is it actually? It actually is a real picture of something.
It's a dog.
It's really a dog running out of the woods. If you look here, you can see his snout, right? His nose and his mouth, and these are his ears, and this is his tail, right? And you can see his front paw is bent that way, right? It's a poodle, a black poodle, right? So, I mean, this is something that's been on, have people seen this around the internet? Has anybody seen this on like social media? Because people are baffled by this picture. But yeah, it actually is a dog. But I think more people saw it as a man running into the woods because of all of these pictures of men in snowy areas running away from the camera that I showed you. And that's an example of priming, right? People are highly suggestible, and you can kind of put expectations and suggestions into their heads by priming them to see certain things. Okay. So maybe you kind of think, if you're somebody who saw the man, I mean, I saw the man and I wasn't primed to see the man. I saw this, like, my husband showed it to me last night. I was like, send that to me. I'm doing priming tomorrow. But I think your history of pictures that you see has a lot to do with which one you see at the time. So there's a really huge psychological component to your perception, even though the actual physical thing that we all see is the same. And there's actually a lot of research that shows that when people are sad or in a bad mood and you show them a hill or a mountain or a slope, they perceive it as more steep, more precipitous a climb than people who are in a good mood. And that's been replicated many times. So first people report their mood, and if it's a negative one, and you show them a hill and you don't say anything about it, like you have to climb this hill, or you're going to have to live at the top of the mountain, or anything like that, and you just say, venture a guess as to how steep this slope is, and you show them angles, or you say, about how, what degree angle do you think this is, or whatever, and they guesstimate that it's a much steeper angle. All right, so let's move on. All right, so priming is when you activate, usually unconsciously, something in someone's mind that sets them up to perceive something or remember it a certain way. This is a TikTok I was telling you about yesterday. Turns out it was right in my folder for this class. Okay, so
Muhammad, 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 Muhammad.
And then just three.
okay.
Muhammad, 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 Muhammad.
And then just.
Okay, so they're priming her by having her say the name Muhammad, 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 Muhammad over and over again, right?
Muhammad, 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 Muhammad.
And then just three more times.
Muhammad, Muhammad, Muhammad.
What does it say?
Ashmed, or Ashamahad.
What's it say?
Asamahan.
Did you see what it said?
Ashamed.
What's it say? It says a shame.
Okay, so how is that priming? How was she primed?
They had her say like a Middle Eastern name, and then that kind of looked like a Middle Eastern name, and she was trying to pronounce it like that.
Yeah, she was just thinking that way, and and setting it up kind of like an experiment, like say this, say this, say this number of times, and then showing her something that has ED on the end. And then she forgot how to read a very simple word, right? So that shows you the effects of priming, right? Let's see, we're pretty much out of time. So why don't we stop there? And I will see you guys next time. Right?
You.
Thank you.
Thanks.